For this presentation, we'll be focusing on the carburetor and the fluid dynamics that allow it to feed and control the amount of fuel fed to the engine. The two-stroke engine acts as a positive displacement pump that moves air and fuel. A venturi contains two moving parts, a choke, which is used when the engine is cold to restrict airflow. This allows it to vary the air-fuel ratio going into the engine. And when the engine is warm, the throttle is used to change the air-fuel ratio, and the choke is left completely open.
In order to make our calculations much simpler, we need to make a few assumptions. First, we assume that the flow of air through the throat of the venturi is both inviscid and treated as an ideal gas. Second, we assume that the viscous losses that occur between the fuel reservoir and the throat are negligible because the distance between them is fairly short. Next, we assume that the temperature in the carburetor remains constant. Finally, we assume that the flow rate of air through the choke and throttle plate become negligible when they are closed. To calculate the required pressure difference between the surface of the reservoir and the throat of the venturi, we can use the Bernoulli equation. We take the speed of the fuel at both points to be 0 and the pressure at the surface of the reservoir to be atmospheric. With a known density of gasoline and a measured height, we can calculate the required pressure difference between the top of the fuel reservoir and the throat to be about 1.884 psi. Since we assume the mass flow rate through the choke is 0, we can analyze our system as a control mass when the choke is closed and the throttle is open. After measuring the volume between the throat and the piston, we can use the ideal gas law. With constant mass, gas constant, and temperature, it is possible to develop a ratio between the volumes and the pressures. We can then calculate that the pressure difference that this stage creates is 2.647 psi. When both the throttle and the choke are open, we can again use the Bernoulli equation to model the pressure drop when there is a speed increase along the streamline of air. We know that the velocity will increase when the area decreases due to conservation of mass. So then we can use these relations to calculate the minimum intake speed of the fluid to be 0.476 inches per second and the minimum speed at the throat to be 1.3 inches per second in order to create our pressure difference. When the choke is open and the throttle is closed during idling, we can use similar calculations to when the choke was closed and the throttle was open. We would just use a different volume and we would calculate that the pressure difference created is 2.722 psi.
Shown is the gas tank. The black line is the fuel line. This leads all the way to the bottom of the tank where there's a fuel filter. This fuel line is connected to the fuel inlet port on the carburetor, and the fuel filter allows it to filter out particulates while letting gas through. This animation shows the flow of fuel through the carburetor and into the venturi. In green are two diaphragms. On the downstroke of the piston, there is positive crankcase pressure, which is then transmitted into the carburetor. The diaphragm flap feels this pressure and bows outwards, transmitting positive pressure to the opposite side. These diaphragm flaps act as one-way valves, and these are fuel vanes. On the upstroke of the piston, the negative pressure in the crankcase causes the diaphragm to balloon upwards, creating a negative pressure zone. This closes this one-way valve and opens this one, allowing fuel to flow in. Once we reach the next cycle, more fuel flows in. However, on the downstroke, the positive pressure causes fuel to be pushed back and stopped at the one-way valve. In the next cycle, we see that fuel can finally be pushed through, and fuel eventually reaches the needle valve. On the upstroke, air is sucked into the engine, creating a negative pressure zone near the throat, which causes this diaphragm to be sucked inwards. This diaphragm pushes down on a lever, opening up the needle valve. Once fuel flows into the metering chamber, fuel can then be pulled into the throat and into the engine. When designing a carburetor, design fuel vane, idle jet, and main jet diameters so that your carburetor is capable of supplying the necessary amount of fuel under the most demanding conditions. Although we've not touched on this today, adjustment screws will allow for fine-tuning of fuel delivery under any conditions.